Isn't that great? Isn't that wonderful?
Computers are stupid.
We did figure this out earlier this week, but that was an amazing video on dark matter.
Oh, great. Thank you.
Yeah. How much
It was a lot of fun.
did you guys like that? You guys can hear him okay, right? Everybody can hear Fraser. Absolutely wonderful video, actually. That was pretty informative.
Great. The next one that I just finished writing is all about the upcoming flyby of Ultima Thule with New Horizons and the plans to send another spacecraft back to Pluto. So, pretty interesting ideas there. After that, what am I working on after that? The Ice Cube neutrino detector.
Yeah, that's going to be a big one.
Yeah, that's going to be great. Sort of talk about what neutrinos are and Ice Cube. And then after that, we're going to talk about Hayabusa.
Hayabusa.
2.
Yeah, that's the, in case, and correct me if I'm wrong, that's the Chinese space station?
No, Hayabusa is the Japanese.
Japanese.
Yeah, spacecraft that is currently at asteroid Ryugu.
Oh my goodness, that's right, because they've been talking about this. Didn't China make another space station though?
They're in the process of making their competitor to the International Space Station.
Yeah.
So, and have invited countries around the world to join them to be a part of their space station.
Yeah, that's right. Because there was two things that I wanted to. Yeah, I got some press releases about Hayabusa, and then so I'm mixing information that I read previous to this starting up. Great. Suzuki Hayabusa, formerly fastest production bike.
I don't think it's the same thing. Maybe.
Yeah. And actually, so I had people asking about Zubrin and the
no news. So I think, in retrospect, trying to do a live event with me that close to the Mars Society meeting was a bad idea. So I'm sure we'll set up another time in the future. I've got a bunch of people coming up. I'm going to be gone next Monday.
Mm-hmm.
I'll be down in Seattle watching Jacksepticeye with my children.
Mm-hmm.
And then we'll be back. And then I've got Joe. Who have I got? No, I've got Anton from What Da Math is going to be joining me. And we're going to simulate solar systems and stuff. And then Joe Scott is coming. And I've got a bunch of other cool guests. So lots of good stuff coming. And then on Friday night, tomorrow night, actually, Trevor Jones and he's from Astro Backyard, and we're going to do telescope live stream. So similar to what we did here on your channel, but over on the YouTubes. So,
Awesome.
And I got way better. I did a live stream last night with the telescope, and I think I must have gotten through 50, 60 objects really quickly, very smooth. So I feel like I finally understand the telescope. So.
Yeah, I know, and there's going to be room for improvement with me on that as well.
No, it's great. It's a lot more fun to do this with other people, right? To do it with an audience where you can actually talk with them. And so Trevor is a really skilled astrophotographer, but he's going to just hang out, and we're just going to talk about gear and talk about technique, and at the same time, he'll tell me what kinds of stuff he wants to see, and I'll point the telescope at them. So it'll be fun.
And guys, there's his information. You should definitely hop on over. So he does live stream on YouTube. He has been bringing some of this over to Twitch, but YouTube is his home. But he is bringing a lot of this over to Twitch, which is awesome because we're going to have the Science and Technology channel in, I'm guessing they're aiming for mid-September, but I'm just, we'll see. That might be delayed a little bit, but I bet by the end of this year that will be a thing. So.
Yeah, and that's what a great move to break up IRL into some reasonable sections. And it's a real commitment for them to actually have a science section. So I like that.
Yeah, and I think it's going to be great because we're going to have people that are like, I never knew this existed on Twitch, because people don't think this exists, and it most certainly does. And again, huge thank you to you for the sharing the virtual star party. And we're going to be doing that again, guys, the next 2 weeks. So next 2 Wednesdays. We'll be doing that, and that will be so much fun. Again, those were amazing. Is Dustin going to join us for those, do you think?
I don't know. I'll ask him. I'll invite him.
Yeah, please do.
He had such a great time last time.
He loved chat. Yeah,
he really loved how busy the chat was. And I mean, if it's going to go to the homepage again,
it will.
I'm sure he'll want to be a part of that.
Yeah,
and,
it will.
Yeah, that'll be great.
I've been
And I found a
advocating.
bunch of new great objects. So
Oh, did you?
yeah, I found a bunch of stuff that I hadn't ever imaged before. So
What was one of your favorites from the other night?
well, last night, so I did the Cocoon Nebula, which I had never done. I did a much better version of the North American Nebula, which I actually think I can give you.
Yeah, I can show you guys.
Sure. And again, these are all fairly short. And then I just essentially I picked a constellation. In this case, I picked Cygnus, which is known for having a lot of really great nebulae and star clusters and that. And then I just went through it, object after object after object. Just, is this any good? Is that any good? Is this any good? So we found some really weird stuff. The Fetus Nebula, which I had never heard of before.
Great.
So yeah, I know. But once
they have some really funny names for these nebulae.
Yeah,
they do.
So it was, but it was all good. Yeah, here we go. Let's see. So this was the North American Nebula that I got last night, which again, Carl, my wife tells me to stop apologizing because people think they're cool. But for me, it's like, oh, it could be so much. I mean, it's such a short exposure. It could be so much better. But
I wouldn't apologize. I'm not going to ruin it. I'm not going to ruin it, but I'm going to take away both of our faces because this is incredible for people to see. I don't want to ruin it.
Not the Large Magellanic Cloud.
I know, not that. This.
Yeah. So that's what we did last night.
No big deal.
No big deal. Yeah.
I'm sorry. Cool. This is space porn.
Yeah. And again, it's a 5-minute exposure. Like,
that's gorgeous.
Yeah, it's hard to believe how quickly this thing takes pictures. It's ridiculous.
I mean, look at how much detail you have too. So you do have those dark molecular clouds here. I mean, you can see these hotter regions, guys. I mean, oh my God.
Yeah, and that's just one single exposure, color camera. And again, I think we talked about this last week. Dustin, after doing that first night, is just like, I gotta make this better.
Yeah, no, so I'm leaving this up as the background right now because this is this is way better. Yeah. There's no simulation. This is real space, guys. Is that dark matter? Is that dark matter? No. No. The universe is stupidly huge. Yeah, it is. It definitely is. And so that's insane. I'm sorry. I'm still looking at it. I'm trying to not look at it. I need to look at you, but this is amazing. So this was a 5-minute exposure. So longer than what we were doing. We were doing like 1 minute, right?
We were doing about 3-minute exposures. Okay. And so what I did last night was just went object by object and just said what makes it look good and what makes it suck. Mm-hmm. And so if the image didn't look great, then I did a bit of a longer exposure, and then I just kept going again and again until I'd sort of dialed in what to do. And I found that I can do like a star cluster in about 30 seconds. I can do any individual stars in about 5 seconds. And then if I want to do planetary nebula, it takes about a minute. And then if I want to do something that's fainter, like one of these big nebulae or a galaxy, then I need 5 minutes. And so, the trick is to just like talk.
And we're fine with that. I can. Yeah, that's where it's nice to have people and to wait it out with you and chat also. Star cluster. So someone just said, and this goes along the vein of what we just watched, and thank you again for showing us that sneak peek, guys. He's going to upload that later. So anybody that was here previously, you got to see something that nobody's seen yet.
Yeah, the 4K version is still rendering, so it's not even done cooking yet.
Yeah. And someone says, so how can you say that isn't dark matter? Talking about those molecular dust clouds. I bet you at least $5 there's dark matter in that picture. So I'm going to say, I'm not saying that there isn't any dark matter, but I'm going to tell you that's not dark matter as we know it. Do you want to tell people what we know about dark matter, even though we just went over that? We just went over that, but
is there a way I can tell you that in video form?
So I'm thinking, well, no. So there's no. But what we know is that it doesn't interact with the EM, right? It doesn't, right?
Yeah. So I mean, like one of the ideas, as you said, there's a bunch of those dark nebulae in that picture that are obscuring the light of the stars that are behind it. And it's not that there aren't stars there, it's that there is dust and material that is in between that's actually obscuring the view. There's a satellite there if you see. And so what that means is, and this is one of the things that astronomers tried to look for, right? They realized that those dark clouds give off a very specific signature in radio waves. And so they then used that fingerprint to then scan these larger galaxy clusters, and they didn't see additional dark clouds. They just saw what you would normally see just looking out into space. It's only when they specifically scan one of these dark regions do they actually detect this radio signature. So this was a thing they thought of, was like, maybe it's just clouds of dust that are obscuring our view and hiding what's really going on. And that this was one of the things they tried to rule out.
Yes, because our galaxy has this dark matter halo around it. So while everybody's like, well, galaxies are, they're flat, right? Or some of them are, not all. But if you want to include dark matter, you really wouldn't say that it's flat. With that nice bubble around it, right? That's keeping those stars from the outer portion of the galaxy from flinging
that was
out.
the thing, right? Was that you wouldn't, just like the solar system rotates in a way that where like Mercury goes around and around and around really quickly, while Earth goes around more slowly, and Pluto goes around incredibly slowly. And it's those motions that are that tell you that the gravity of the sun is doing the work of keeping those objects moving around.
Right.
But in something like a galaxy, it looks like the whole thing is just moving as a disk. And that's the part that was really unusual. And the only way to account for that is if the galaxy itself is embedded in this much larger cloud that's slowly turning.
Yeah, that kind of assists things along, because we thought that those outer, just like you said with the Pluto analogy, that those outer, stars on the outskirts of the galaxy, those would be moving slowly, but we didn't see that. Yeah. Which is really, really weird. So dark matter is friction without the friction, someone asks?
I don't understand what that means. Dark matter is causing gravity, is something is generating gravity, and that whatever that thing is, it clumps and it moves around, and there's different amounts of it in different places. Like, it really looks like it's some kind of particle, and yet it doesn't doesn't emit light, it doesn't block light, it doesn't bounce into regular matter, and it doesn't bounce into itself, and yet it behaves as if it is there. And this is why it's such an enormous mystery.
It becomes a superhero. So so someone says, what's the difference between dark matter and dark energy?
Well, and it's too bad that they have very similar names, right?
Right.
Yep. Dark matter is this thing that we just did the whole episode on, and we've been describing, right? Which is this seems to be some kind of invisible particle, or maybe we just don't understand how gravity works at large distances. While dark energy was discovered back in 1998, and astronomers were trying to do this survey of various supernovae, and they were calculating the distance to these various supernovae to try and figure out how quickly the universe was decelerating, right? So if the universe at the beginning with the Big Bang, it started its expansion, and then because of all the mutual gravity of all of the objects in the universe, you would expect the universe to be sort of slowing down and coasting as all of this material is trying to gravitationally attract everything together again. And the question was, would it just keep on coasting to the point that it would just over infinity would finally coast to a stop, or would it go to a certain point and then the gravity would hold everything together and pull it back down into this big crunch?
Right.
And what they found was really surprising, that not only was it not doing either of those, actually, as the universe was getting older, the speed of these various galaxies was accelerating. So and they came up with this term dark energy. And what it really is that there is some kind of expansive pressure that is just appearing in every cubic meter of space that exists in the universe. You get, and it's a tiny, tiny amount, but over vast distances, it becomes the dominant energy in the universe. So this stuff could be very well appearing here in your room, but because of the gravity of the Earth, because of the atomic force holding your particles together, because of the gravity of the solar system, it's not going to make anything expand. But when you get to large enough distances where you've got the Milky Way and some galaxy that's 100 million light years away, then dark energy is a stronger repulsive force that is pushing these galaxies apart and eventually and accelerating them away from each other, and they will never connect. And so eventually, far into the future, you're going to have these regions that where the gravity was stronger, and they pull themselves together into these gigantic clusters, and then the rest of the universe will be accelerating away from us and will fall over the cosmic horizon and disappear from our view. And future cosmologists will only know about the local galaxies around them and have no concept that there was ever the Big Bang and that there was ever cosmic microwave background radiation. It's kind of amazing that we live in this time that we do in the universe.
Yeah, we're pretty lucky.
Yeah.
It's a good time right now.
Yeah. I mean, we missed the party. We missed the
Right.
big party, which
did.
was a few billion years after the Big Bang, when all of the star formation was happening and everything was really cooking. And but at least we're not at the point that sad, depressing future when you don't even know that there's such a thing as
That there was a party to miss.
Yeah, there was a party to miss. There was ever such a thing as a larger universe. Yeah,
there's a party you didn't go to. You'll never know.
They wouldn't be able to see it.
Right, and it's so true, because we're a third. They say a third generation star, so that means that we had a few stars that had to go before us to get the star that we have in the metallicity that we have within our star. Which, you guys, it's a fancy word for saying anything other than hydrogen and helium. We deem everything else after that just metallicity. Those are metals. So
yeah, metal. Yeah, hydrogen, helium, metal.
Right. Hey, Master Coupon. So let's see. I read given what I read in the YouTube comments on Twitter, that would make sense if you're using to Ozzy just said that this is very esoteric and crazy, but what if dark matter is consciousness?
Whoa.
I know.
Dude. I can see my hands.
Bro.
They're as big as the universe.
So let's see. It makes sense if you're using if you use it to explain why it looks like all other galaxies moving away from us. Yeah. So again, just to summarize, I like to say, as far as dark energy goes, and you heard Fraser say it too, something repulsive. It seems to be a repulsive thing, whereas dark matter seems to be the opposite of that. It seems to attract things, to bunch things up, to clump together, and gravitationally is what we see. So those are two opposing things in my brain. But again, we are on the verge of breaking science with all of this stuff. This is why it's so cool.
And that was the point of my video. Was you're popping in to, you're asking scientists, how's it going with that whole understanding the universe thing? And they're like, oh, we've got this weird mystery and we don't know what it is yet. And you're like, cool, keep it up.
Great. Yeah.
Great.
And then Dr.
Let me
Paul,
know when you solve it.
Then Dr. Paul's like, yeah, there's this thing called strange matter. And I'm like, that's great. Can I not have any more things that I can't tell people anything really about?
No, they just keep popping up. And if you don't have those mysteries start showing up, then you got a problem. Right. Then you're nearing the end of science.
Right.
But until then, you want to have more mysteries than you always want to have more mysteries. You want to have every answer generate more questions.
That's the goal of science in my mind too. So future astronomers won't see what we see today. What if dark energy or dark matter is the remnant of the universe's past? Basically, we're late to the game, and dark energy is the galaxies our future can't see.
Well, the thing is that we can see right to the beginning of the universe. We can see to about 300,000 years after the Big Bang. So we look out in all directions, we see galaxies speeding away, but we're also able, because of the cosmic microwave background, able to see what the universe looked like just a short period of time after it formed. And so, no, we are lucky that we do get a chance to actually see back in time as we look farther out into the universe. It's the future astronomers, when the cosmic microwave background disappears, fades away until it's undetectable, when the most distant galaxies are moving away from us faster than the speed of light and fade away and are become undetectable. That's when you will suddenly not know where you are, right? It's the difference between sitting on a boat in an ocean, in the middle of the ocean, and not being able to see any land masses around you and know anything.
Right.
And as opposed to being in a bay and seeing landmarks all around you that you can look at, except you're not looking back in time when you're doing that. So
Right.
but
Right.
still.
Exactly. So Cable says, when I was at school years ago, what we were taught was that matter, there was always antimatter, and there has to be an equal amount of both. So these are different things, antimatter and matter, and you're talking a little bit more about cosmology and annihilation, how we actually ended up with more matter than antimatter. That's actually still a question too.
Yeah, it's still an open question. Nobody knows, right?
Yeah, no.
Why was there more matter than antimatter in the universe? The thing that we know now is that the universe is dominated by matter, and there is no antimatter.
Yeah.
Apart from the occasional stuff that's generated by, various supernova explosions and there are various events that can generate antimatter, lightning strikes, things like that. But it will usually find a particle of matter and annihilate again. But it's weird. You would think the math seems to say that back at the beginning of the universe, there should have been exactly equal amounts of matter and antimatter.
Yeah, and
there wasn't.
And someone asked a question, so antimatter equals dark matter, but DPI gave a pretty sufficient response saying no.
Yeah,
antimatter definitely interacts with matter, and in a very violent way.
Yeah, when matter and antimatter interact, there is no question that they just did, right? They annihilate in the most perfect way possible, generating pure gamma radiation equal, based on E equals mc squared. So if you take a kilogram of matter and you mash it together with a kilogram of antimatter, you get E equals mc squared's worth of gamma radiation, which is a very easy thing to spot. It's very bright. So we don't see that. We look out into the universe and we don't see the annihilation of matter and antimatter. It would be very obvious. So those distant galaxies that we see, they're all just matter. And whatever dark matter is, it doesn't behave like antimatter or regular matter.
And someone said, wait, can lightning generate antimatter?
Yes.
Yes. Guys, that equals yes. Because that's actually pretty cool. I learned about that recently too.
I don't know the exact process,
right?
But you do search for lightning antimatter, and you'll find a bunch of articles about it.
Okay. So, how true is it?
I don't go into more detail.
No. I
physics process there. Right. I'm sure.
Yeah.
As soon as I do an episode on it, then it's all in my head.
Yeah. How true is the theory of angels and demons with matter and antimatter? We'll consult Tom Hanks in his upcoming movie. Just so you guys wait.
I haven't even seen that movie.
I haven't either, but that's where my brain went.
Apparently they cover it.
We'll just refer someone to possibly not anything that has to do with anything. Guaranteed it doesn't.
But I'm going to assume that it's completely wrong. I don't need to even see it, but I've got to assume that it's completely wrong.
And let's see here.
That's safe.
Yeah, that is safe. We were also taught that Pluto is a planet. Okay, so Pluto's
Poor Pluto. This is funny. So my latest episode, I'm talking all about Pluto, and I don't mention planet or dwarf planet at all.
Oh no!
I just call it a world. I call it a Kuiper Belt object, but I'm not even going to engage in the debate.
Oh, wow.
I don't think anybody notices.
Yeah. Well, nobody watching here now. You guys will all go to that, and you'll be like, "We noticed."
You won't notice.
Yeah. What Hollywood gets right all the time.
Yeah, exactly. Yeah, Hollywood always gets it right.
Yeah, absolutely. But yeah, I think dark matter and dark energy, having those two things, being as ominous as they are, which obviously we know more about dark matter, relatively, compared to dark energy. Having those names, they always confuse people.
Yeah.
And I agree. There's a lot of people in here like, why don't you call it invisible matter?
Yeah, I mean, it doesn't matter, right? And I guess it's funny how the name, people seem to really grab onto the name,
Yeah.
while something else, a name that is maybe more complicated or more technical, people have less interest in those kinds of things. And so, but it is really funny to me, and this was sort of what I was trying to get at with the video, is just how people have this gut response.
Yeah.
Dark matter, I don't like it.
I like it.
Like, I don't like it. What did why'd you have to go make that up?
Uh-huh.
Well,
Oh yeah. Yeah. No, they don't like it. They don't want to
Yeah.
believe it exists. Just close to gravity,
Yeah.
But
Yeah, and it's a funny thing. Like, that's a human psychology thing that I find really fascinating. And there's something there.
yeah.
And they'll often follow up with a completely unsubstantiated theory of everything, which shows how Einstein was wrong. I get a lot of those emails. I'm sure you do too now. Einstein was wrong. Here's how. I've, in my mind, come up with a way to fully explain the universe.
Yeah.
Great.
Actually, gravitational lensing was just another one of the things where we were like, that guy was right again.
Uh-huh. Yeah.
And that's one of the ways, again, we detect this stuff is gravitational
Einstein
lensing.
was right.
Einstein was right. Again, I was so many times this guy, and I hope that we, in these upcoming generations, either in mine or the ones thereafter, I hope if we have someone thinking like that. I wonder if the grand unification, I'm guessing you're talking about guts, the grand unification theory, will shed light on dark energy.
Grand unification, like, this is the hope to try and merge, or to try and connect gravity and quantum mechanics.
Yeah, it's
right.
Real tough.
Yeah, really tough. You put one equation into the other and you get gibberish, and you put the other equation into the other and you get gibberish, right? But yet both of them perfectly, exquisitely explain various parts of the universe. So that's tough and frustrating, and this is why people are developing all of these theories to try and figure out how to unify gravity and quantum mechanics, and so far have been completely unable to. And that's what string theory is about, and that's what loop quantum gravity is about, is this attempt to try and bring those two theories, each of which are clearly very well explain what we see in the universe. So be nice to be able to figure out a way to make those connect together. Will that explain how the universe works, how dark, who knows, right? But at least you'll know how gravity and quantum mechanics work with each other, which, I mean, it'd be Nobel Prizes all around. They'll just rain Nobel Prizes on whoever does that for decades.
Yeah, and so,
like, I know you won the Nobel Prize last year. Here, have another one for this year.
Right, and so you said the LHC, so the Large Hadron or Hadron. A lot of people say it different. I think I say Hadron, but
Large Hadron. How do I say it?
You say
Large
Hadron.
I say Hadron.
Yeah, but I honestly, I've heard it both ways. So what they're doing with detecting dark matter is essentially creating creating energy, right? That's
Yeah, well, I mean, it's
there.
funny. The way particle colliders work is so fascinating, because we know that via E equals mc squared, we know that energy and matter are really just different versions of the same thing. That energy and matter are interchangeable. You can turn energy into matter, and you can turn matter into energy. Obviously, a way you could turn matter into energy is you take matter and antimatter and merge it together, and you get gamma radiation. Boom, you just made energy out of matter. But the way you go the other way is really fascinating, right? Which is that you take particles, you put them in these particle accelerators, and you speed them up to enormous velocities. And what you're doing is you're essentially taking the mass of this particle, and you are imbuing it with an enormous amount of energy, of kinetic energy, right? Because it's a particle moving very quickly, so that although it might just have a tiny amount of mass in it, because it's moving at close to the speed of light, it has an enormous amount of energy. And when you smash these particles into other particles, all that energy is in this tiny little space, and it needs to go somewhere.
Right.
And so it freezes out into physical particles in that moment because the energy was packed in too tightly and now it can't go anywhere. And so you get these little particles appearing essentially out of nowhere, but they were there. They were just that they were frozen out of the amount of kinetic energy that you put into the particle when you smash them together. And this is the way. And so you can calculate. You go to, like, we move a proton at this speed, we put this much energy into it, we smash it into something else, we expect this cascade of particles to appear because the math holds, right? You know, if you can do some fractions and you've got this much particles left over, you can know we're going to get, you've got, it's like your budget, right?
Right.
And so they're at a point now with the Large Hadron Collider that they have found all of the pieces of the standard model that they were expecting to see. The Higgs particle was the last one that they were expecting to see, and then they haven't been able to find anything after that. And so now they're probably moving to a part where they're going to brute force. So they're literally just going to go and accelerate a proton up to a certain speed, smash it into particles, see what happens, tweak it one more notch, try again, see what happens, tweak it again, see what happens, and just keep ratcheting up the amount of energy to try and find something new, because every attempt to find anything now that has been explained by particle physicists has failed.
Yeah.
So now they're in completely unknown territory. It's a pretty fascinating sort of, it's a dilemma.
Right.
I mean, it's weird because they found everything they were expecting to see, and the disappointing thing is they didn't find any of the things that would have helped particle physicists move to the next level.
Right. And the Higgs boson, that was really exciting. I remember people getting so excited about it. And then we found out, oh, by the way, there was some faulty wiring.
Yeah.
We need new theories for the LHC to disprove.
Yeah. And this is one of the things that they do, right? Is that the various physicists are trying to work on these ideas of how to extend the standard model. And they go, okay, we think there's this thing called supersymmetry, and you're going to expect to see these particles that are the symmetrical pairs of all of the particles we understand. And you should see the first particle here at this point, at this level of energy. And so they crank up the LHC to that level of energy, smash particles together and go, nope. And then some poor researcher has to throw out all of that work because their prediction failed, which is, they're fine. They love to do that. They can't wait to have their theories thrown out.
Right. Someone just said that, because then this is good. You cancel that out, right? It's back to the drawing board.
That's how science works, right?
Right.
And I mean, we deal with that in computer science when we're looking for a bug. Maybe it's this function. Nope.
Yeah.
Right.
And I guarantee it's probably just as frustrating.
Yeah.
Debugging's not fun.
No, but you are narrowing it down and trying to figure it out. So.
Yeah. And someone said the Higgs decay witness was just published. Okay. So Fraser, how easy is it to pass peer review and get something published?
I don't know. I've never tried. I'm not a scientist.
Well, having talked to many scientists, or maybe I've talked.
It depends. It depends on which journal you're going after. It depends on. So there's a whole bunch of things that go into it. Like people publish to Astro PH to archive all the time without it going through peer review. And then if people want to get into, say, Nature or any of those big journals, they do have to pass peer review. I don't know how much of it is politics and how much of it is really legitimate, severe.
We'll just say that Dr.
Review.
Pamela was like, so it's great that it got published. That's what she just, these are, I guess this is a little bit more something that can happen. And it's ideas that come from that, right? So that's kind of, again, the whole thing with science is to throw ideas out there, see what catches. If someone else is working on something and they can say, oh, wow, that helps with this. That's so it's, I haven't heard about that. I'm not saying it doesn't exist, but wasn't the proposed collider that was canceled in
Yeah.
America actually even higher energy than the
Yeah.
LHC? Did that
The
send?
superconducting super collider.
Yeah.
And in fact, there's still tunnels of it in the US that you can go and explore. I've seen people find these abandoned tunnels they go into, and they can see the remnants of the superconducting super collider. And it's so sad that the US never built it, because it was going to be far more powerful than the LHC. And the United States decided they didn't want to do it anymore, and instead collaborated with Europe, which I guess, I like collaborations.
Yeah.
And it's the same thing with fusion. Is the United States just completely gave up on fusion research at the large scale, and passed along that responsibility to the Europeans. So they're building ITER. There's the Stellarator in Germany, and then the Chinese are doing a lot of work in fusion. And the Americans do have some fusion projects, but the really big system like ITER has been canceled. So it's too bad.
Yeah. Did you see that question by DPI regarding? I don't know if you have the chat up.
DPI, was it back?
Yeah, just a little bit. Can
levels?
we even research sufficient energy levels for higher energy particles? Is that even, possible?
Yeah. So yes, this was the point of the superconducting super collider, was that it would be a much larger ring, more power, higher energies, allow you to probe farther into the particle space.
And Ice Cube, is Ice Cube gonna do something in that realm as well?
Well, Ice Cube is a is a
Neutrino.
natural detector, right?
Is it?
But the
Is it
trick with
gonna?
Ice Cube is that it is under a kilometer of ice,
Oh, right,
so
right, right.
it's blocking the cosmic rays, which are these really high energy particles that are being transmitted. But the one that is going to be able to do that is the AMS on the International Space Station. And I mentioned that it's detected something like 90 billion cosmic rays.
Mm-hmm.
And these are generated by supernovae, or supermassive black holes, or colliding neutron stars, or I don't know, it's still a bit of an unknown.
Mm-hmm.
And they are much higher energies than anything we could ever hope to generate here on Earth. And it is this natural, it is the end result, right? So imagine there are these natural cosmic rays being generated by these events, and it's as if you had a particle accelerator. You just couldn't control the energy that went into it, so you just got whatever came your way. And they're colliding into this detector on the space station, and then they're looking for various cascades of particles from there. So it's a pretty great instrument, and a great way to go about it, because it's a way for you to take advantage of these really higher level energy.
Yeah, and also at dark matter and ways to detect it. I know you mentioned gravitational lensing. There was WIMP detection, and also the LHC, and there was other ones. The Fermi gamma ray space telescope? Isn't that another way that they're kind of looking
Fermi
into that?
it's, as you said, it's gamma rays.
Right. Yeah.
So they're not going after cosmic rays. Cosmic
Right.
rays are particles. Gamma rays are just electromagnetic. It's on your arm.
Right. Well, here's the thing. So with the gamma rays, I thought they were able to probe into, looking into dark matter with that space telescope.
I don't know specifically. Yeah, but
Yeah,
you'd have
because
to tell me.
yeah, that one. Well, these are things that I recall from a while ago, but and also haven't WIMPs kind of lost. In case you guys don't know, that's the weakly interacting particles that we were talking about. We have machos and we have WIMPs, which is great. And that's a great way to talk about astronomy. In fact, I remember those things because of how my astronomy teacher at the higher level was describing these things. But these weakly interacting massive particles, is that still holding out pretty good, or has there been any?
Yeah, I mean, it's funny. There's actually a big controversy that
Yeah.
has been blowing up on Twitter in the last couple of days, where folks like Ethan Siegel are on the one side saying the evidence for particles is overwhelming, and then on the other side you've got people like Sabine Hassenfelder
Mm-hmm.
saying no. It's definitely not conclusive, and it could very well be something in between, that we don't understand gravity and there's some kind of particle that is causing this interaction. So it's still I wouldn't say it's I mean, if you go and talk to 20 dark matter researchers, I think you're going to find most of them are going to be now moving towards that it is a particle because of a lot of the detections that they've made, and a lot of the things like the gravitational lensing, the signal in the cosmic microwave background, things like that. And yet the fact that they haven't been able to actually detect a particle is, is really, that's the kicker. So like once you detect that particle and it matches what you're expecting, then it becomes a slam dunk. But
Mm-hmm.
until then, there's no real sure proof that it's a particle.
Yeah.
And then, again, this is like this welcome to the being in the middle of a mystery.
Mm-hmm. Mm-hmm. And there was another good question. Well, not a good question, a good remark. And this is what I've heard too. Nalu says the reason a lot of bad science gets published or spread around is because there's a lot more publications of people to peer review them, so tons of stuff slips through. Yeah, that's kind of what I've heard, is that it's not too hard to get something published nowadays. And
It depends on the journal.
It does depend on the
there
journal.
are some journals that are very, very careful, and there are other journals that will let anybody publish anything.
Mm-hmm.
And then they get humiliated when someone publishes something. I think, the whole journal system is in great need of an overhaul and in great need of disruption. And there are a lot of really interesting online communities trying to find ways to crack the journal system to make the information more easily. Because right now, like, I don't know about you, but like I try to go and find information locked in journal articles.
Oh yeah.
And you just hit this paywall, and I'm like, I'm not going to spend $1,000 to report on a story.
Right.
Right. And so I tend to just not. And yet it's not like I'm going to be doing the research. So there's definitely, and I think a lot of researchers are very frustrated because the science is paid for by taxes,
Mm-hmm.
and it should be publicly available for other people to work with, and yet it doesn't.
Right. No,
It's
that's
hidden behind this paywall.
extremely, yeah,
And
it's
the journals
extremely
say, well, we're
frustrating.
spending all this money. It's all of this, we're having to invest all this money and time into doing this work, and so we should be able to profit from it. So it's a big frustration.
Yeah, no, it is. It is. I agree. Anything that can further knowledge. Yeah, I agree. Absolutely. And oh, so Kendu is asking. He says the moon doesn't rotate, but we found out that his first language isn't English. So yeah, tidal locking.
Does the moon rotate? I believe was the question.
Yeah, does the moon rotate?
Yeah, the moon rotates, right? The moon takes about 28 days to show every different part of its surface to the sun.
Mm-hmm.
So you can call that what you want to call it. That is rotating, right? You are. If you were standing on the moon and you were staring at the Polaris, you would see Polaris over the course of 28 days. Or any other star but Polaris, actually. Although I wonder what the North Pole of the moon is facing at. But anyway, if you were staring at the sky, you would see the stars make one circuit around on the axis over the course of 28 days. That is rotating, right? The fact is, just from our perspective, the moon doesn't look like it rotates because it is tidally locked to us, and so it always shows the same face to the Earth. But if you're standing on the moon and you're looking out into space, you will absolutely see the constellations, the stars turn above you over the course of a month, over the course of 28 days.
We're rotating. It's rotating. We're just in a nice little harmony that when we rotate, we see that same side.
Yeah. everything. So imagine two kids, right, are holding arms and they are spinning around with each other. Are they turning? Right?
Yeah.
So if one kid looks at the other kid, the kid doesn't appear to be turning. But if you're standing and watching them, you would say, yes, they are turning.
Yep.
So it's all your perspective.
Mm-hmm. Interesting analogy. I like it. I actually really like that one. I'm a rookie here, but what is the end result of those research tests? What does the search for particles tell us if we find the right result? What does it explain? Or is the answer to this the answer they are searching for? Nightwalker, that's a good question.
Well, so I guess the question is like, what is the point of science?
Right.
Right? Why do we try to understand how nature works? Sometimes we just want to understand nature because it helps us. It fulfills our curiosity.
Right.
These are fascinating questions and we want to understand them. And then in other cases, you get things like phones because you figured out how to make transistors. So, and you won't know in advance which one those is going to be, whether you're going to find out some esoteric, interesting piece of information about the universe, or you're going to find something that's actually applicable and turns into technology or helps us understand diseases or things like that. So, right, the theory of evolution is that us just being curious about the way life works here on Earth. Well, it turns out it actually has a practical purpose too, with disease resistance and creating our own agriculture and things like that. So,
and again, like I like just to go back to what you were saying earlier, some of these things are to give us questions that we didn't know really existed at the point that we're doing this, and I say we as a collective, as humanity, there's research out there that actually will develop further questions that we didn't know were there until we got to that point to have that research and be like, oh, maybe we should ask this question. We didn't know that question maybe initially. So so our whole
modern society has all of the benefits because of science. And nobody really knew in advance which things were going to be the important ones and which were going to be the things that were a waste of time. It's only by just being curious about every single possible thing that you can find does the whole machine move forward. And here we are with electricity and the internet and phones and modern medicine and airplanes and spacecraft and telecommunications, GPS, and all this stuff. Each one of these, and lasers, so much from lasers. Each one of these is just the result of people researching and following their curiosity, and then other people realizing that this technology could have some practical application to make our lives better. Or worse.
Or worse. So that goes, Bagheera said, how can AI help us understand the universe? Well, he just listed some things right there. There's some technology. Also, machine learning, these things are happening. In astronomy right now. These are new tools. There's I forget who we had on here. Who was developing a lot of machine learning for looking, because there's copious amounts of information that we're getting back from some of these missions, and having something be able to have the algorithm to go through and peel through those patterns and pick those up. It's critical.
They're finding extrasolar planets. They're finding galaxies. They're finding all kinds of really interesting things in data, things that in many cases require a human brain. Up until this point, computers are terrible at, but now AI is actually getting pretty good at being able to sift through enormous amounts of data and find things, and it's just going to get better and better.
The moon is going away 1 centimeter, roughly.
Goodbye, moon.
Roughly an inch a year, roughly, but it's nothing you need to worry about. That I will tell you. Don't even worry about it.
Well, someone else mentioned in the chat, right? It's going to take about 50 billion years, and eventually the Earth and the moon will lock to each other, and then it'll stop drifting away. But also then the sun will be dead and we'll have crashed into Andromeda. Who knows what's going to happen.
The universe will be at our doorstep just saying, hey, I exist, by the way, humanity. Can we push the moon closer with nuclear weapons?
Sure, but then it'll just go farther again. So you can just delay.
Some of Fraser's responses, just the sure.
Yeah, go ahead, do it. Make it happen. Take the entire. So I forget who did it. Somebody did a great. Scott Manley, I think, wanted to say, like, if you fired all the most powerful rockets on the Earth, could you change the Earth's rotation speed? And the reality is, you could just like a fraction of a fraction of a fraction of a fraction of a second on a day. There's so much energy required, built up in these systems to try and change the orbit of the moon. is just like, you could let off a whole bunch of nuclear weapons and it wouldn't do anything.
Yeah. Is Venus tidally locked to the sun? No. Actually, no. Venus is rotating backwards and very slow. In fact, Venus will go around in its orbit around the sun before it experiences a day.
You can walk faster than the Terminator moves on Venus. So you can actually be on the surface of Venus, and you could walk with the sunset around the entire planet. Now, of course, you would be dying in sulfuric acid, atmosphere, carbon dioxide, 93 times the atmospheric pressure of Earth.
No big
Temperature is hot enough to melt lead, but you could do it in your Venus suit. Yeah. And even, so you're probably questioning about tidal locking because you would think Venus obviously is closer into the sun. Even Mercury is not completely tidally locked. It's a 3-2 resonance. So it rotates 3 times every time it goes around. So every 2 orbits, it rotates 3 times. So very it's
weird.
Entirely possible that it will lock at some point in the future. And you do, a lot of those planets that are around the red dwarf stars, like TRAPPIST, the TRAPPIST system, those planets probably are tidally locked
all of
to
them.
their star.
Yeah.
The moons of Jupiter are all tidally locked to Jupiter. As long as you get a very strong gravitational object and other things fairly close to it, you're going to get that tidal locking.
Yeah, and
Pluto
Mercury's
and
weird,
Charon
though.
are locked to each other. I think Titan is locked to Saturn, so you get this all the time.
Yeah, but Mercury's weird. If you were standing on the surface of Mercury, right, you could see the sun rise, right?
Yeah.
Go back down, rise again. Mercury's been a puzzle for Einstein, Newton. These are Mercury's weird, but it makes cool patterns, guys. Have you ever seen a spirograph?
Especially when it's in retrograde.
Let's see. You'll destroy the atmosphere before you slow the spin of Earth. I'm just questioning.
Yeah. Well, if you did that of Earth, but I don't know if Titan is locked. Let me see.
Yeah, I'm not sure about Titan.
Let me find out.
Titan's cool still, though.
It is tidally locked to Saturn.
Yeah, I miss the spirograph. Yeah, me too. I miss Etch-a-Sketches.
Understand Mercury, understand the universe.
Seriously, Mercury is very, very weird. But I think we were talking with you about it. Like, Mercury could be kicked out, right?
Yes.
Mercury could.
Jupiter. People think too highly of Jupiter. They think that Jupiter's got our back. Jupiter does not have our back. Jupiter would be glad to kick any other planet out of the solar system at any time.
But doesn't that make him the best?
It throws asteroids and comets at us, and has done so in the past. While also absorbing a few. It took a few hits, but it has also thrown a bunch at us. So it's still I
would say you don't want to trust it.
An unsolved question. Yeah, you definitely don't want to thank it for what it's done for us in the past, because what it could have done is smashed us with asteroids.
Yeah. Isn't there another moon found around Saturn last spring? So here's the deal. We find in moon,
moons all the time.
Moons happen all the time. Moonlets even more common. So moonlets are smaller than moons. But this happens all the time. So as far as the gas giants are concerned, you can just go ahead and say that number is, we know with Jupiter is you got the 4 Galilean moons, right? Those are enough to have the hydrostatic equilibrium. They're locked. They're there. We know they're there. They're not going anywhere. But as part of the moonlet system goes, I mean, Jupiter can take something that comes in from the Kuiper belt or from the Oort cloud, and it's like, hey, you're my moon.
Yeah.
Or it could toss it our way.
So they just discovered, what was it? Another
11
10
or something?
moons,
10,
12
11?
moons or something like that just a couple of months ago.
Yeah. And it ruined what Space Engine said, which it said it had 69 moons, which was great for teaching astronomy. Okay. Now that's been ruined because that's an easy number for a good portion of the population. But now I have to be like, yeah, it's 69 plus 10 or 12. Okay. So write that one down, guys. Jupiter the Disruptor.
So you can guaranteed there are more moons. Now they're going to be really tiny.
Yeah, moonlets.
For both. And they're guaranteed to be more moons for Uranus, Neptune. They're out there.
Yeah. And but like, you know, Ganymede's bigger than our own moon, and that's one of Jupiter's the Galilean moons. Ganymede's bigger.
Yeah. They thought that they originally thought that Titan was the biggest moon in the solar system, and then it turned out that Titan actually has a fairly thick atmosphere, and that was confusing them. And so then they realized that in fact it's Ganymede is the biggest in the solar system.
Yeah. Well, I read one is close to our moon size. I know
there are ones that are the moon. Our moon, I think it's like our moon is like the fifth largest moon.
Yeah, we've got a good sized moon. We've got a respectable moon, but again, that's a part of Earth, right, guys? I mean, our planet was very nice, and it was like, I'm just going to create a moon, but it happened through a pretty violent process. Let's see.
Can I give you another picture?
Of course, absolutely.
It's
it doesn't like it because Discord. By the way, guys, Discord. You guys, just in case you're seeing this background, okay. This is something that Fraser, he did last night. So you guys have seen us do the virtual star parties. We will be bringing those back on the 5th and the 12th. Yeah, I'm trying to pull up the calendar. So yeah, the 5th and the 12th, we'll be doing the virtual star party. Again, so for September, if you guys, those will be later streams. So if you're in the EU, you know, that's going to be a challenge, but we will be doing that. This is a picture in the background. I'm going to take our faces away just so you guys can see it again. These are pictures that he took last night. This is a 5-minute exposure that he took last night with a telescope, and we're going to be doing that. Are we going to be aiming for planets potentially while Saturn is still out and beautiful?
Not yet. So until we get a planetary scope, we won't be able to do that.
Because Saturn's out and Saturn's super cool, guys. But you know, this is obviously, these are deep sky objects, and they're amazing to look at too. Yeah. And you can see the detail here. So we're stuck with Saturn for now. Yeah, we are. But we're gonna have those again and again. Huge thanks to Fraser for
and thanks to Dustin and Oceanside Photo and Telescope for letting us use that amazing scope.
And Dustin will hopefully come back. I hope he does, because he was a blast. He really liked chat, by the way, guys. You guys were your usual selves, which is mostly wonderful. I'd say 99.1% wonderful. We need a robot arm to hot swap the robot telescopes. So this is going to be a thing that we're going to do. Obviously, Fraser has, he does travel and do other things. Astronomy Cast, by the way, is going to have their 500th episode. Yeah. Guys, Astronomy Cast. I was actually playing that in the car on the way back from breakfast this morning, just being like, you have no idea how crazy it is that I know these people that I've been listening to, and here I am now collaborating and talking with them. And without these guys, you wouldn't have me. So that's it. It's a huge inspiration, and I'm truly fortunate. When does the Very Large Telescope, the VLT, begin construction in Chile?
Well, the VLT already exists.
Yeah, we already have stuff with the VLT.
The extremely large telescope, I believe it's going to be finished in 2026. So it's not that long. Did you get the new picture?
There it is.
I just sent you a picture in Discord.
You did. Let's see. Open original. Wow. Everybody can see it. So I'm not saying wow. I'm not saying wow without. I'm going to take our faces away though again, because this is beautiful space.
So see if anybody knows what it is. Can anyone post in the chat what it is?
Ganymede is bigger than Mercury. Yeah. Is Saturn always visible at night? It is not. Not at least here in the northern hemisphere. It's not a thing. Or in the southern. No. It comes out.
It's the Pelican Nebula.
Did someone guess it? Someone said lagoon. Orion's belt?
No.
Pelican.
Needs more saturation. It's got a lot of, yeah, maybe. I mean, I just did a really quick little process on it. This is what I'm not good at, is processing my images.
These are beautiful. The Pelican Nebula, let's see how far away this bad boy is. About 1,000, yeah, 1,800 light years away. So you're looking at, that's pretty amazing. But I still think the detail, look at those stars. So guys, you know, if in case you're new here, and it's totally fine that you might not know this information, but this is in our own galaxy, because again, we have a galaxy with, you know, 100,000 light years from top to bottom, or if you want to be super fancy, you could say 125,000.
Yeah.
But you can go ahead and just say 100,000. You're fine.
Yeah. So no,
cool.
Still can't do planets yet, but Dustin's working on it. We'll get there.
Yeah, we'll get there. And guys, Saturn is quite the sight to see. But
so just a reminder, though, we're going to be doing this again on tomorrow night over on my YouTube channel at 8:00. So if you actually go to my YouTube channel right now, there is you actually saw it on my YouTube channel, has what's the upcoming live event, and that's going to be the one tomorrow night where Trevor Jones and I are going to work with the telescope, chat about how to take pictures, gear. He's way more knowledgeable than I am about actual telescope gear. So
8 p.m. what time zone? I'm guessing you're talking about Pacific.
Pacific time, yeah. When it gets dark for the telescope.
When it gets dark,
it's almost dark.
Yeah, definitely. I'm bringing up his YouTube right here. So yeah, if you guys want good science, like this is a tried and true. You're not going to get fake news. Someone can actually break it down, explain things in a small segment of time, and actually do a good job. And that's, you know, I sit here and live stream, and yeah, that's exhausting on its own. But having something like that, that's tough to do, believe it or not.
So last week I was on the channel. Now it's time for me to go, but I noticed that you only had like some fraction here, that you're doing some kind of math below your face. Yeah. Where it says like 5 out of 10. Mm-hmm. And we were able to make that number into like a whole number. Yeah. Yeah. So what's it going to take for that number, that sub goal 5/10? To turn into a larger number? And so here's the thing, right? By supporting streamers like Sky, you are battling the ASMR. You are battling the nonsense and pseudoscience that's going on. Sky's not going to do your horoscope. She's going to teach you science. And I think it's really important for people, if science education is important to you here on the internet, and to battle against the nonsense and the pseudoscience and fill the world with positive information, serious science information, then you should take a second. It's only $5 and support Sky in what she's doing here. Give her some money, donate a membership to somebody else, and help her help other people learn about science.
That's pretty much it. It's like the Tom Cruise phrase, like, help me help you. Yeah. Yeah.
Yeah. It's just like, what kind of, again, we talked about last week, what's the world you want to live in, right? You want to live in the world where people rub ears and talk about, lip smacking noises about what they're hearing? Is that what you want this part of Twitch to be? Or do you want some science? You want science. So, and just think, like, the more donations she gets, the more she can be able to do more of this full time.
Yeah, so. It is true. It is true. And I appreciate you saying that. Yeah. So someone just gifted 5 subs. And then
perfect. We did it.
We did it. And also Recro came in too and subbed to help out. So thank you guys. Awesome. I appreciate it. And thank you.
You are making the world a better place.
I'm trying.
Not you, them.
Oh.
Yeah. Well, also you, but them.
Yeah. All right. Well, thank you. And we'll see you next Wednesday.
Yeah. I'll put that in my, can you, I don't think I see a thing on my calendar. So
I can have Joe, the amazing Joe, send that on over. And so guys, next 2 Wednesdays, we have the virtual star party, and we'll have Fraser on too. And then he's going to go away and do other stuff, but we'll still be watching his videos.
I've got a gigantic file to upload to YouTube now.
Yep. Do you mind if I maybe play it again later too?
Of course.
Okay.
Yeah, absolutely. Yeah. So clear, you got free use to publish anything of mine at any time whatsoever on your channel. Go crazy.
Same. All right.
Right on.
Thank you.
All right.
Have a wonderful
All
day.
right.
All right.
See you
Bye-bye.
later, everybody.